Hello friends. So, we have seen the Gauss-Seidel and Jacobi iteration schemes for implementing the iterative solvers. So, those are very simple matrix multiplication and a series of matrix multiplication with recursion of previously computed solution going back to in the computation to generate the next iteration, next improved estimate, and slowly the methods these techniques they gradually converge to the true solution, although the rate of convergence is very slow as compared to the methods that we will discuss now, but still they provide us the basic idea, basic structure and basic feel of how the iterative schemes actually work and why it is advantageous, because all that we need is a simple matrix multiplication routine and we only deal with non-zero elements of matrix A, because there is no point in storing something as 0 and then computing multiplication of something with 0 as 0. So, we can that does not affect any of our computations whatsoever. So, we use with iterative schemes we make use of sparse storage, and using sparse storage schemes we implement these using standard matrix multiplication algorithms with the proper addressing mechanism using data structures that are used and implement these methods. So, the next method that we discuss is the method of steepest descent. So, in this case the system of equations A x is equal to b can be viewed as the solution of an equivalent minimization problem. That is, we minimize a functional of vector x given by a quadratic functional. So, half of x transpose A x minus x transpose b. So, if we minimize this with respect to x, then the solution is of course A x is equal to b. The minimization is going to be A x minus b is equal to 0, the first derivative of first variation with respect to x being 0. So, that is the condition of minimization with respect to x. So, that vector x which will minimize this functional pi would correspond to the condition that first variation of this quadratic functional with respect to x should be 0. So, that is the condition, and necessary condition for minima is that the vanishing gradient. So, delta pi as a function of x should is equal to A x minus b, and that should be equal to 0. So, null vector. So, gradient vector, this gradient vector that we have, gradient of this functional pi. So, this points in the direction of increasing value of the functional pi. So, I mean that is our standard definition of a derivative. Gradient is a derivative. So, dy by dx, the positive sense as we increase with respect to variation of y with respect to x. So, that increases, that indicates the positive sense is that it is a positive gradient. So, the function value is increasing with respect to x. So, the gradient vector, it will point to the increasing value of functional pi with respect to the vector x. So, if we are interested in decreasing the functional value, because we need to minimize, the whole idea is we have to minimize the functional. So, the decrease, if the gradient vector points to this increasing value, the decrease will be in the opposite direction, and that is what gives us to the solution, leads us to the solution. So, we should actually come down the hill. So, gradient actually points to upward the hill, let us say it is a the functional pi represents a hillock, and the gradient vector at any point x points to the upward direction towards that hill. And so, the negative value of the gradient that is computed will point to the decreasing down the hill direction. So, how much we should move in that direction? because it may so happen that at that point this one particular direction we have the steepest decrease, most rapid decrease in the functional value, but that will continue only up to certain point. After that it may be some other direction which is decreasing the functional value at a more rapid rate. So, that is what we call as line search, how long we should move along this descent line. The direction opposite to the gradient, that is negative of nabla pi, points to the direction of steepest descent, steepest decrease in pi in the neighborhood of point x, and gradient is of course negative of gradient is of course the residual vector that we had defined earlier of the residual vector of the system of equations. So, that also serves as a monitoring or tracking of the convergence of equations. So, going down the hill, so this is what it looks like. So, for any particular iteration, let us say the trial vector or the solution is represented by this vector x in ith iteration, and this is the complete space of n number of variables, real numbers, and a times x I points is a vector pointing in this direction, and b is a vector which is pointed in this direction. So, this r I at the ith iteration. So, the error in solution in ith iteration is this particular vector, and this is what tells us that we should nudge the solution in this direction, which will take us the shortest possible way to meet the vector b. And how far do we go in this direction? I mean this length, how do we measure this length? What should be the length of our step? That is what we use as the line search algorithm. So, assuming any trial vector, initial vector x 0, the residual is r 0 given by b minus a x 0. So, matrix vector multiplication and subtract it from the right hand side. The updated solution by moving in the direction of steepest descent is x 1 plus is equal to x 0 plus alpha 0 times r 0. So, this alpha 0 is the step length in the direction of r naught. So, r 0. So, this is the how much should we move along this particular direction in one iteration. So, that we keep on moving on the steepest descent, what the most rapid decrease in the functional value, we move in that direction for the time until it is the maximum reduction possible. So, to find this step length, we force the new residual to be orthogonal to the previous residual. So, this is only possible when there is no further decrease possible. So, that means the error, all that we have already accounted for all that is there to be gained in this direction. So, there is no new information that can be accommodated from this direction by following this particular direction. So, new additional information in the representation of expansion of the basis is possible by following this direction. So, when we do that, so the new vector is this, and from this we can estimate what is the new residual r 1 going to be as a function of alpha naught alpha 0, and once we have r 1 we enforce that the new residual should be orthogonal to the previous residual. So, that we have explored all that is possible to be explored in the previous search direction, and the new search direction should be orthogonal to the previously searched direction. And that leads to, so when we enforce the orthogonality condition, that is projection of r 0 on r 1 is 0, and that leads us to the condition for the step length, alpha 0 is just a ratio of two scalars r 0 transpose r 0 divided by r 0 transpose a r 0. So, a r 0 is simply the matrix vector multiplication. So, new search direction, the residual vector is again obtained as simply by previous residual previous search direction is modified. So, r 0 minus alpha 0 a r 0. So, that is the new search direction that is available, and then the new solution is computed as x 1 as x 0 plus alpha 1 r 1, and then the iterations continue in the same way recursively until we reach the norm of residual becoming lower than the acceptable norm. So, the formal algorithm we can list down as a sequence of steps. So, going down the error hill. So, we keep on going down the hill. So, we start with an initial estimate, initial guess for the solution vector x 0. The residual is estimated, r 0 is estimated as b minus a x 0, and that is the gradient, negative of gradient, and we save this matrix vector product because this is used very often. So, then there is no need to reinvent the wheel again and again, and we can save this matrix vector multiplication in a vector and use this vector wherever we need to use this matrix vector multiplication. So, determine the maximum step length along the direction line search r 0 as alpha 0 is equal to r 0 transpose r 0 divided by r 0 transpose q 0. So, q 0 is the vector that we stored as matrix vector multiplication a r 0. So, for each subsequent iteration j, let us say ith iteration. So, this is how it starts, and for each subsequent iteration we keep on updating the search direction and compute the step length. So, update the solution vector. So, previous solution multiplied by whatever is the step length multiplied by the residual vector or the search direction, corresponding search direction, and that gives us the new updated solution. And with this new updated solution we have we find what is the residual vector. So, residual vector is again related to previous residual vector and minus this matrix vector multiplication and step length. So, that gives us the orthogonal residual vector to previous vector, and if this residual vector, new residual vector, norm of new residual vector is less than certain fraction of initial residual, first residual, for some pre-specified value of epsilon, it can be very small number, then we stop the iterations, or else we proceed with the next iteration with updating the vector q. So, q I for ith iteration is given as a times r I. So, residual of ith iteration, and step length in ith iteration is computed as r I transpose r I divided by r I transpose q I, and we again go back to computing the next iterate, next value of the residual vector and the updated solution, and the cycle proceeds until we compute the up to convergence. So, this is a very decent improvement in convergence, and I mean dramatic, actually dramatic improvement in convergence compared to Jacobi or Gauss-Seidel iterations, and for particularly well behaved and well conditioned system of equations with small condition number, the method actually converges very quickly. But there is a problem here, that for some system it is quite possible for the method to get locked down into the two search directions only. See, the condition that we impose here, orthogonality condition. So, this orthogonality condition is only for two consecutive search directions. So, it may so happen that R 1 is orthogonal to R 0 and then R 2 will again be computed as orthogonal to R 1, which will be in the same direction as R 0, and then the improvement is not really as expected, because we have already traversed the direction of R 0. There is nothing more to be gained there, but there is nothing in the algorithm to prevent traversing in R 0 direction again, because the only thing that is imposed here is the new search direction should be orthogonal to the previous search direction. Now, that previous search direction could very well be what has been traversed earlier as well, and if that happens, then there is no way to improve upon the solution, and it gets locked into these two direction, and that way the solution will actually suffer. We may not actually go beyond certain limit. I mean, after a while the residual will stop decreasing, and once that happens, if that is monitored, then obviously there is a need to restart the entire process again. So, to address this particular problem, that we may get locked into two directions, two mutually orthogonal direction, and we may alter the algorithm may alternately switch between two directions, and with no further improvement in the computed solution. So, the key point is straight way down is not fun, it may get locked, I mean, between two directions. So, method of steepest descent offers a dramatic improvement in convergence over the Jacobi and Gauss-Seidel iterations, but there is nothing in the algorithm to prevent searching for solutions along the directions previously explored, since the orthogonality is imposed only on two consecutive search directions, and when we do that, then previously searched directions could be traversed again. There is nothing to prevent that from happening. A faster convergence can be achieved if independence of a search direction with respect to all previously searched directions is enforced. So, if we have some mechanism in which the new search direction is guaranteed to be independent of what all has been done earlier, then we are looking at possibility of developing a basis for expressing the solution, and that is what is achieved, that is what is aimed at in the method of conjugate gradient. So, method of conjugate gradient for symmetric matrix, if matrix A is symmetric, that is a very simple algorithm. For non-symmetric matrices also there are versions of conjugate gradient method available, but those are little more tricky, little more difficult to understand. But for if the matrix A is symmetric, then it is the algorithm is very straightforward. So, it is based on making a direction A conjugate with respect to previous direction. And how does it help? So, what is done is, instead of saying that matrix or the direction R 1 is orthogonal to R 0, I would rather impose that direction, new direction R 1 is orthogonal to A R 0, a very minor seemingly very minor adjustment, but with this has a lot of theoretical basis to ensure independence of the search direction. This simple A conjugation allows us to enforce that the new search direction is always guaranteed to be a direction which has not been explored earlier. So, the first step is identical to that of the steepest descent. So, let us say first search direction, let us say P 0 is same as that of the steepest descent, that is B minus A x 0, and updated solution is given by x 1 is equal to x 0 plus alpha 0 P 0. So, alpha 0 is again the step length, how much we should go along P 0, and the new residual is given by R 1 is equal to R 0 minus alpha 0 A P 0. So, that is the first step. So, first step is common with steepest descent, because that is the first operation we are doing. The step length alpha 0 is determined by enforcing orthogonality of the new residual with respect to previous residual. So, again first length, this step length is determined in the same way as the steepest descent. So, no change here, except that we will in practical implementation we will be replacing A p 0 with vector q 0. New search direction P 1 is taken in the span of R 1, that is it is going to be a linear combination of the new search new residual vector R 1 and previous search direction P 0. So, that is P 1 is going to be R 1 plus beta 0 P 0. So, that is a linear combination of two vectors. So, it is the spanning of new residual R 1 and the previous search direction P 0. So, R 1 plus beta 0 P 0, and beta 0 can be estimated from the A conjugacy of search direction, that is P 1 has to be orthogonal to A P 0. So, that is P 1 transpose A P 0 should be equal to 0, and when we substitute this P 1 as this, it gives us an equation for beta 0 to compute this length factor beta 0 as negative of R 1 transpose A P 0 divided by P 0 transpose A P 0. So, what has happened here that is different from previous I mean steepest descent? It is this conjugation and the fact that previous direction is taken as the span of the previous two residual vector and previous search direction, and that we will see how that makes a difference. So, the updated solution now looks like x 2 is equal to x 1 plus alpha 1 p 1, and the new residual is now if I substitute it back, and the new residual is going to be b minus a x 2. So, and x 2 is of course this. So, I can expand this. So, b minus a x 1 plus alpha 1 a p 1, and a x 1 is again x 0 plus alpha 0 p 0. So, I can substitute it back, and then if I expand it all in terms of a r 0, then it becomes r 2 is essentially what I have here is r 0 minus alpha 0 a p 0 minus alpha 1 a p 1, and how is that different? What does it mean? So, next search direction we will see how this expands, how this term expands with each iteration. So, the next search direction P 2 is obtained as span or linear combination of R 2 and previous vector search direction P 1. So, R 2 is equal to or P 2 search direction P 2 is equal to R 2 plus beta 1 P 1, and beta 1 is again obtained from the A conjugacy, that is P 2 transpose A P 1 should be equal to 0, and that leads to solution beta 1 is again obtained in the similar fashion as a ratio of two scalar products, and solution proceeds in the similar manner with one line search and one A conjugation being performed in each cycle. So, composition of each search direction. So, this is what I meant when I said let us look at how this term expands. So, first search direction is R 0, second search direction is R 1 plus beta 0 R 0. So, R 1 is R 0 plus alpha 0 A P 0 plus beta 0 P 0, and that is essentially is equal to R 0 and A R 0. So, P 0 is same as R 0 in this case. So, what we have here is the new search direction is a linear combination of R 0 and A R 0. So, this A R 0, the linear combination has forced this vector to be away from R 0, and this will keep on happening, and this will keep on adding more and more powers of A, such that if I expand for the kth iteration, the search direction is a span of a linear combination of R 0, A R 0, A square R 0 and so on up to A raised to the power k R 0. So, individually these are all independent vectors, because this is essentially matrix multiplication of a vector in force, I mean that is like rotation of a vector. So, vector R 0 is being continuously rotated, and therefore, these are all independent directions, and this is what we know as a Krylov subspace. So, in this by ensuring this A conjugacy, what we have been able to achieve here is that the search directions are always independent, and the algorithm would then, because obviously for an n dimensional system we do not need more than n number of base vectors. So, the algorithm should converge in at most n number of iterations, n number of steps. So, the moment we have n number of independent vectors here, the solution is complete. So, there is no further iteration, but unfortunately this is fine as far as theory goes, and this is obviously independence works assuming infinite precision arithmetic is at work. But for floating point operations with large powers of matrix A, the directions begin to lose independence and the convergence suffers. So, that is an implication of limitation of floating point arithmetic. Nothing wrong with the algorithm of conjugate gradient, but because we have to implement this on a digital computer with its own vagaries of floating point operations, the Krylov subspace that we try to generate, the base vectors may start losing their independence, and then the convergence slows down or convergence takes a hit. So, what happens is after k plus 1 steps, k plus 1 independent search directions are included in the solution updates, and so just enough to uniquely identify any arbitrary vector in k plus 1 dimensional space. And this is generally referred to as generalized class is generalized minimum residual method. So, GMRES, and this should lead to exact solution by using only matrix vector multiplication, provided that we are working with infinite precision. But for finite precision, search directions lose mutual independence for higher powers of A. We will see that in our next lecture how this happens, losing independence for higher powers of A. And the solution to prevent this or prevent this loss of independence is to use Gram-Schmidt orthogonalization periodically to restore mutual independence of search directions. So, after a certain number of steps, we orthogonalize all the vectors using Gram-Schmidt orthogonalization, and that will provide the previous basic independence of the search direction. So, if there is any loss of independence because of higher powers of matrix A, then those would be set right by using Gram-Schmidt orthogonalization. So, once we have this, so Gram-Schmidt orthogonalization on its own is a very expensive process. So, it should not be used indiscriminately. So, a judicious call is required to implement Gram-Schmidt orthogonalization after certain number of steps have been taken, and to set the independence of the vectors again in the solution process. And with that, the although initially when it was conjugate gradient method was proposed, it led to a lot of excitement in the community that it looks like a iterative scheme, but it is a exact solution, because theoretically you have as many base vectors as are required to represent any vector. So, we should be able to compute exact solution, but the finite precision arithmetic, they actually prevent the independence of the search direction in Krylov subspace that is generated, and gradually it was realized that fine there is a limitation due to finite precision arithmetic, but it can still be used as a iterative solver, and that is with much better convergence characteristics than steepest descent. And with this modification of Gram-Schmidt orthogonalization thrown in between two subsequent directions, and that will ensure the convergence of the conjugate gradient method. And with that, we close this discussion of solution of linear simultaneous equations, and we will now move on to the discussion of eigenvalue problems. So, iterative schemes, again I repeat, they are very popular and very powerful, and particularly conjugate gradient and its variant, they can make use of very efficient data structure using only non-zero elements of the matrix coefficient matrix stored, and that can lead to very effective and very fast computational scheme. Thank you.